Some of these problems where you're reviewing activities with rational functions are a little bit more than you need to know, but just make sure that you can add rational expressions that have different denominators. That's what this is. Make sure that you can simplify compound fractional expressions. This next problem is just a more complicated version of the other two, so I'm not real concerned about that. This one is an exercise with rationalizing the numerator of an expression. I'm not real concerned about that. However, you should be able to rationalize denominators. So we have this problem. You would multiply by the conjugate, which would be 2 plus the square root of 3 over 2 plus the square root of 3, the conjugate over the conjugate, using the multiplication property of 1. This one, this second exercise, I think should have had a square root symbol on the 3 there, so you have an actual irrational denominator to rationalize. So the multiplier here for 1 would be the square root of 3 over the square root of 3. You can use the negative square root of 3 or the negative square root of 3. Either one of those would work. But I want to focus on the asymptotes in this section. Remember that asymptotes are, I guess I don't really need that. Asymptotes are vertical or horizontal. First of all, the vertical asymptotes are the vertical lines that pass through the values of x that are not in the domain of the function. So you look at the denominator of the rational expression, you set that denominator equal to 0, and that's how you find the vertical asymptotes of your function. And those are exactly the same x values that are not in the domain. So the question, find vertical asymptotes and find the domain of the rational function, actually are the same type of question. You do the same exact thing. You have a domain restriction for rational functions when the denominator is equal to 0. You also have a vertical asymptote where the denominator of the expression is equal to 0. So here for the rational function 1 over x, we see that we'll have a vertical asymptote when x equals 0 because x is in the denominator as a single term there. So the vertical asymptote is actually the y-axis, which has the equation x equals 0. Okay, rational functions also have horizontal asymptotes, and the horizontal asymptote is related to the end behavior of the function, and that's, remember, the behavior that is exhibited by the function as x becomes increasingly large, either positive or negative. So the end behavior of a rational function is where we get the horizontal asymptote, and you can see that for the function r of x equals 1 over x, if x is becoming increasingly large, 1 over x is going to simply become smaller and smaller. Whether it's positive or negative, it doesn't really matter. It's going to approach 0. And so what that means is that as the values of x become increasingly large in the positive direction, the function values, you can see the y values, are actually coming down the y-axis, and they're crowding in at 0. They never actually get there. So you can see that the distance here, the height of the function, this placement there, is getting smaller and smaller and smaller, and that's because the y values are getting closer and closer to 0. Same thing happens as x approaches negative infinity. This time the y values are coming up the y-axis, so they're in the negative part of the y-axis, so these are all negative values, but again they're crowding in at 0, and you can see that by looking at these segments which give you what the length of y is, and those are getting smaller and smaller because these points are crowding in at 0. And so we say that the end behavior is as x approaches plus or minus infinity, y approaches 0. And that's what gives us the horizontal asymptote, which in this case happens to be the x-axis, which has the equation y equals 0. So we'll look at more horizontal and vertical asymptotes, but we also did a little bit of a review here. We reviewed a little bit with transformations of graphs. This first one, s of x equals 3 over x plus 1, is just a horizontal transformation 1 unit to the left of the graph of 1 over x, followed by a stretch, a vertical stretch of 3 units, so it's pulled up. So you can find the transformation of the second one here, t of x, and I'll let you do that on your own. What you need to do is perform the long division of 2x minus 3 divided by x minus 2. And I know that we did this in class. So you take x minus 2 and divide that into 2x minus 3. And when you do that, you get 2. Let me see, 2 times x is going to be 2x, and 2 times minus 2 is minus 4. Now remember, when we are doing long division, the next thing we do is subtract. So we're going to subtract 2x and we're going to subtract negative 4. So those signs change. And that gives us a 1 here, and that's our remainder. So it's 2 plus 1 over x minus 2. I know that's hard to see because it's written over the letters there. So it's 2 plus 1 over x minus 2. So what we have here is a shift to the right of 2 units. Okay, shift to the right of 2 units, followed by a vertical shift up 2 units. So the graph of 1 over x would be shifted to the right 2 units and then up 2 units. So what I want you to do is figure out what the new vertical asymptote and horizontal asymptote, and maybe even look at the y-intercept and the x-intercept if there is one or are any for that one. In fact, when we get to this next exercise, that's exactly what we'll do. We'll look at all the intercepts and the asymptotes, and we'll sketch the graph, and we'll talk about the domain and the range. So let's see how this one would work. We have, first of all, we see that if we want to look at x-intercepts, that's where does the graph cross the y-axis? Crosses the y-axis when y is equal to 0, and y is r of x. So 0 equals 18 divided by x minus 3 squared actually has no solution. There's no number you can divide x by to get, no number you can divide 18 by and get 0 for an answer. So there's no value of x that will make 18 divided by x minus 3 squared equal to 0. No solution means no x-intercept. Now let's look for a y-intercept. Y-intercept is, of course, what you have when x equals 0. So we'll set x equal to 0. That means we're going to find r of 0, because that's where x is. Well, that's 18 over 0 minus 3 squared. 0 minus 3 is negative 3. Negative 3 squared is 9. 18 divided by 9 is 2. And so that means when x is 0, y is 2. And so 0, 2 is the y-intercept. What about horizontal asymptote? Well, the horizontal asymptote is the end behavior. So let's think about 18 over x minus 3 squared. Well, as x becomes increasingly large, either positive or negative, it doesn't matter, you're going to square something in the denominator. So that's going to be a large positive value down there. And the numerator is always just 18. So it just stays 18, but the denominator gets very large. So again, we have a horizontal asymptote at y equals 0. The vertical asymptote is exactly the value that makes the denominator 0, and that's x equals 3. We put all this information together. We can sketch the graph. We know we have a y-intercept at 0, 2, so here it is. There's the y-intercept. We know we have a vertical asymptote at x equals 3, so here's 1, 2, 3. Vertical asymptote I'll sketch in with a dashed line. And we know that the function is always positive valued because it never crosses the x-axis, and therefore we know that the function's graph must look something like this. That's one branch, and then the other branch for the values of x that are greater than 3 goes over there. So we have a nice symmetrical graph here, and it's characterized by the horizontal and vertical asymptotes. So just keep in mind that rational functions typically have horizontal and vertical asymptotes. Here's one where we have a vertical asymptote at x equals 3 and a horizontal asymptote at y equals 0. Here we have a vertical asymptote at x equals negative 2 and a horizontal, oops, that's not the horizontal asymptote. The horizontal asymptote for this one is at this level, which is y equals, looks like 3. And then finally, we have a vertical asymptote here at x equals 1, and a horizontal asymptote at y equals 1. Okay, so just keep that in mind. We actually did this exercise in class, and we found out that for this rational function x over x minus 2, rational function x over x minus 2, we completed each of these tables. Now remember, you can do this on your TI calculator very, very quickly. First, make sure that you do table set, and that's the, make sure I'm spelling this right, table set, T-A-B-L, it's actually TBL-SET on your calculator. It's the second function of the window key. So on table set, you want to have independent variable set at ask so that you can ask the calculator to put in a particular value of x. The independent variable is x. And the dependent variable, you want that to be auto, so the calculator will automatically calculate the dependent variable, which is y. So when you do that, put this into one of your functions in your y equals area, your equation editor. Put x over x minus 2. Make sure that you put x divided by x minus 2 in parentheses, otherwise the calculator will follow order of operations without parentheses and you'll get some surprising results. So once you have the function entered into the equation editor, you can fill in these tables. And I want you to do this on your own. First of all, notice that in tables 1 and 2, we have the x values that are getting close to the number 2. In table 1, the x values are getting close to the number 2. Here's the number 2. All these x values are less than 2, so they are approaching 2 from the left. And remember in class we saw that we write that as x is approaching 2 from the left with a raised negative symbol behind the 2 to indicate that we're approaching 2 from the left. In table 2, the values of x are all greater than 2 and getting closer to 2. So these values of x are getting close to 2 from the right. And we denote that notationally by writing x is approaching 2 with a raised little plus sign. This should be a little arrow right here. I'm having a little trouble with my stylus. But this is just notation that helps us to keep in mind that what we're doing is approaching 2 from one side or the other. So in either case, as you enter these values for x in tables 1 and 2, you will get certain values for your r of x column, and you can make a conjecture about what you think is happening to the y values. Well, you can also tell that from just looking at the function, and you see that 2 is not in the domain. So what's going to happen is you're going to have a vertical asymptote. So you should get some pretty recognizable values there to make a conjecture about where the y values are going. In tables 3 and 4, we're actually allowing x to grow without bound. And so in table 3, we see that x is getting big in a positive sense, so we're approaching infinity. In table 4, x is getting big in the negative sense, and so we're approaching negative infinity. So you want to see what the end behavior is for this, and of course that will tell you what the horizontal asymptotes are. So work that out and make sure that you can figure those out and make your conjecture about what the vertical and horizontal asymptotes are based on those tables. This leads us to the actual definition of vertical and horizontal asymptotes. After you've worked with them for a while, the definitions are a little easier to understand. So what you should do is, since I know that by now you've probably done quite a few problems, now go back and look at these definitions and make sure that you can understand the mathematical verbiage in those definitions after you've had some experience. And similarly, for finding asymptotes of rational functions, we have this process where we can find vertical asymptotes by simply looking at the zeros of the denominator, and we find horizontal asymptotes. There are actually 3 cases as listed here. If the numerator has degree less than the denominator, equal to the denominator, or greater than the denominator degree, that will determine where the asymptote is. But actually, I like to think of this as end behavior, and if we think of it as end behavior, when we're looking for horizontal asymptotes, we only need to consider the dominant term in the numerator and the dominant term in the denominator. So in this first example, r of x, we see that the numerator has dominant term 6x, that's the only term up there, and the denominator has dominant term x squared. So when x is large, the polynomial or the rational function r of x has the same behavior as the rational function 6x over x squared. But that has the same behavior as just 6 over x by simple reducing of that expression. And of course, when x is a large number, this has the same behavior as y equals 0. And so now we know that the horizontal asymptote is the line y equals 0, which again is the x-axis. So we have a horizontal asymptote on the x-axis. Vertical asymptote is obtained by looking at the domain restrictions. Well, that means we have to look at the denominator, x squared plus 2, and see what real numbers make that equal to 0. Well, there are no real numbers that make that equal to 0. There's no solution to this in the real numbers, and so that means that there is no vertical asymptote. No vertical asymptote for this particular function. Now we turn to x-intercepts and y-intercepts. So first let's look for x-intercepts. The x-intercepts are the values that make the function equal to 0. So we take 6x over x squared plus 2, and we realize that that only equals 0 if 6x equals 0. That's the numerator. 6x equals 0. Well, that only equals 0 if x equals 0. So the x-intercept is x equals 0, and then of course y equals 0. So that means that the x-intercept is the same as the y-intercept. Might not seem like we have enough information here, but actually we have quite a bit of information. We know that there's no vertical asymptote. We know that there is a horizontal asymptote for on the x-axis, and we know that the graph goes through 0, 0. So what does the graph of this function actually look like? Well, a quick check shows that if it goes through the origin, if the x values are negative numbers, then 6x over x squared plus 2 will be a negative number. So the graph has to be in this quadrant. And then if x is a positive number, 6x over x squared plus 2 is positive valued, so that means the graph must be in that quadrant. There's no graph in quadrants 2 and 4. And we have a horizontal asymptote on the x-axis. So that means that the graph has to go through the origin and then go up for a while and then eventually slide back down asymptotically to the x-axis. And similarly, goes through the origin and then goes down for a while, but then slides back up so that it can be asymptotic to the x-axis. And so we see we have these asymptotes, and we have this function that looks I guess kind of like an airplane propeller or something. You can verify this with your graphing calculator, but I know that we have this one correctly done. And so now the next thing we want to do is look at the function s of x, which is this one. First, let me get this a little cleared off here. Clear some of this off. Clear some more of it off. Okay, now we're ready to look at the function s of x. 6x squared plus 1 over 2x squared plus x minus 1. So first let's look at horizontal asymptotes. I guess all we're supposed to look at is horizontal and vertical asymptotes here, not going through graphing and every bit of it. So let's just save some time and just do what we're instructed to do. Horizontal asymptotes, remember, are related to end behavior. So you want to think of a horizontal line and you want to think of x going to plus or minus infinity. So that's how you remember that you're looking at x going to plus or minus infinity, and for that you only need to look at the dominant term in the numerator and the dominant term in the denominator. And so we have that our function s of x behaves just like 6x squared over 2x squared on the ends, which behaves just like 3. And so now we have a horizontal asymptote y equals 3. That's the horizontal asymptote. The vertical asymptote we get from zeros of the denominator. So we look at 2x squared plus x minus 1, and we set that equal to 0. And actually we try to factor because that's our easiest way of solving these types of equations. We know that we have to break the 2x squared into 2x times x. One has to be a plus and one has to be a minus, but they both have to be 1s. And once we put those in there, it's easy to see that we need a plus here and a minus there. And so we actually have two vertical asymptotes. X equals 1/2, the 0 of this factor, and x equals -1, the 0 of that factor. You might want to practice graphing this, figure out what the x-intercept, y-intercepts are. and see if you can come up with anything on that. But it has several examples of sketching graphs of rational functions. We did these 3 in class. And so the process is first to factor, then to find the x and y intercepts, then to find vertical asymptotes, then find horizontal asymptotes, and finally sketch the graph. You can do these 4 steps in any order that you like, really, but I would say factoring should always come first. The first one is already in factored form, so we can find the x-intercepts. The x-intercepts are when y equals 0. Well, since y is r of x, and that's a rational function is 0 when the numerator is 0. And the zeros of the numerator are x equals 1 and x equals -2. Those are the x-intercepts. The y-intercept is the value obtained when x equals 0. So if x equals 0 in this function, we're calculating r of 0. If you were to imagine multiplying these 2 polynomials, multiplying them out, the numerator would be an x squared term and an x squared term, an x term, and then -2. The denominator would be an x squared term, an x term, and then -3. And so therefore, the y-intercept, which is what you get when x equals 0, is going to be 2/3. And so actually, remember that y-intercept is actually 0, 2/3, the point, the ordered pair. Similarly, for the x-intercepts, they're actually ordered pairs, 1, 0, and -2, 0. For our purposes, though, we'll just keep in mind that these are the numbers that we need. 1 on the x, 2 on the -2 on the x, and 2/3 on the y. Those are our intercepts. Okay, the vertical asymptotes are the values for which the function is not defined. And that's the zeros of the denominator. And those are going to be x equals -1 and x equals 3. The horizontal asymptotes are from the end behavior. So we look at r of x. The numerator dominant term would be x squared if you multiplied it out. The dominant term in the denominator would also be x squared if you multiplied it out. And this is just like 1. Therefore, we know that y equals 1 is the equation of the horizontal asymptote. With this information, we should be able to draw or sketch the graph, and then we can verify with our graphing calculator. Make sure we understand these concepts by doing it without the graphing calculator. So the x-intercepts 1 and -2. Here's 1, 2, 3. Here's 1, 2, 3. 1 and -2, so there's an x-intercept here, and there's an x-intercept here. Y-intercept is 2/3, so here's 1, 2, -1, -2, so 2/3 is about right there. Now these are points on the graph. We also have vertical asymptotes at -1 for x and 3 for x, so we'll draw vertical lines dashed through -1 and through 3. Now we see that we have 3 regions where we want to draw our graph. The first region is this part of the plane, the part to the right of this vertical asymptote. Next region is in between the 2 vertical asymptotes, right in between. And the final region is to the right of the asymptote x equals 3. So we know that the graph has to have this asymptotic behavior, and we know that these are the only 2 x-intercepts. And so in particular, in this region, the region to the right of -1 on the coordinate plane, we know that in order to have the correct asymptotic behavior, the graph has to either do something like this, like that, or something like, well, it can't do that. It can't come from up here and go through there because it's got to be asymptotic to x equals -2. That's why I know that the graph must do this in this part of the Cartesian plane. It's got to do that because of the asymptotic behavior and because of the x-intercept right there. So I know that that's what the graph does in that part of the plane. It does exactly this. It has this bend, just like that. For the part of the graph that's to the right of x equals 3, we have asymptotic behavior, and actually, I think I have a little bit of a mistake right here because this isn't right. We have a horizontal asymptote. I forgot all about the horizontal asymptote at, we have a horizontal asymptote at y equals 1. Yep, I need to graph that. So here's the horizontal asymptote. Ooh, I'll make that in blue. Let's make that in blue. There we go. So the horizontal asymptote should go through y equals 1. There we go. This is better. All right, there's my intercept. Oh, that's even better now, because now I have more regions that I have to look at. Okay, so I've got either this this part. I've got region number 1, region number 2, region number 3, region number 4, and region number 5, and region number 6. It's sort of like I have 2 vertical lines and 1 line like that. So these are the 6 regions I'm talking about that I have to figure out where the graph is in those 6 regions. So in this here, that's where the intercept is, right here. So I know that the graph must do this, because it's got to go through that intercept, and it's got to be asymptotic to this vertical line and to this horizontal line. So the graph must do that. Over here and here, I know that there isn't an x-intercept, and I have the asymptotic behavior. That means the graph can't be in this region, because if it were, it would cross the x-axis. So it's got to be up here. It's got to be up there. That's where the graph has to be. What about the central region? Well, since this is the only x-intercept and that's the only y-intercept, and the graph has asymptotic behavior on these vertical lines, I know that it has to do something like this. It has to be wiggling through that central part. It's got to be wiggling through. So that's what the graph looks like, and you can verify that on the graphing calculator. Sorry about forgetting about the horizontal asymptote, but actually you can see where I figured out my mistake, and maybe that'll help you when you get stuck and see contradictions in your work. You can figure out your mistakes too. So let's go to the second problem. The second problem is r of x equals x squared minus 2x plus 1, and so forth. So the first step is to factor that. So let's factor the numerator. And we can only hope it's factorable. So we know we have x and x. We know we have 1 and 1. I guess we need 2 negatives, so it turns out that that's actually a perfect square. If we look at the denominator, in fact, that's a perfect square as well. It's x plus 1 squared. So we have x minus 1 squared over x plus 1 squared. So what does that tell us? Well, let's see. We know that we have it factored, so now let's find the x-intercept, if there are any. Well, there's only one x-intercept, and that's x equals 1. That's when the numerator is 0. It happens to be a root of multiplicity 2, which means that near that 0, the graph is going to have this kind of behavior. It's either going to be a frowny face or a smiley face, I guess is what you want to call it. What about y-intercept? Y-intercept is what we obtain when x equals 0. When x equals 0, we get, looking at the original form, if x equals 0, that's 0, that's 0, that's 0, that's 0, so we get 1 over 1, so we get y equals 1, and that's our y-intercept. Horizontal asymptotes, or the zeros of the denominator. Horizontal asymptote is end behavior, so we're going to look at the end behavior. The end behavior is when x grows increasingly large, so we look at the dominant term in the numerator, which is x squared, and the dominant term in the denominator, which is also x squared, and the end behavior of that is the same as end behavior of 1. Therefore, the horizontal asymptote is the line y equals 1. The vertical asymptote is obtained by looking at the zeros of the denominator. That's clearly x equals negative 1, so we have a vertical asymptote at x equals negative 1. Let's see if we can figure out what this graph looks like. We have x-intercept at x equals 1, so here's x equals 1. We have a y-intercept at y equals 1, so here's y equals 1. That's let's say, a horizontal asymptote also at y equals 1. So this is one where the graph actually intersects a horizontal asymptote, which can happen. Graph can intersect a horizontal asymptote, but cannot intersect a vertical asymptote. The vertical asymptote is x equals negative 1. Here's negative 1, so we'll sketch in the vertical asymptote right there. So what does this tell us about the graph? It's very interesting. We know we have a horizontal asymptote, y equals 1. We know we have a vertical asymptote, x equals negative 1. And we know we have to go through this point and this point. So the graph must come from up there and go through here, and we know that this is a 0 of multiplicity 2, so it bounces off and then goes back up and doesn't cross the horizontal asymptote ever again. Never crosses it again. I'll show you how to verify that in a minute. So that's the branch to the right of the vertical asymptote. To the left of the vertical asymptote, since I know that this is the only x-intercept, the graph can't be crossing the x-axis again. Therefore, it must be up here. That must be where the graph is. So you can look at the graphing calculator and verify that this is the correct graph. Now, as mentioned, I'll show you how you can determine if there's more than one crossing of a horizontal asymptote. Crossing a horizontal asymptote just means that the function, which in this case is right here, x squared minus 2x, x squared minus 2x plus 1 over x squared minus 2x, plus 2x plus 1. If you're going to cross the horizontal asymptote, that means that that y value has to equal the y value of the horizontal asymptote, which is 1. So if we simplify this equation, we can solve it by seeing that x squared minus 2x plus 1 has to equal x squared plus 2x plus 1. And now the x squareds cancel out. The 1's cancel out, and so we end up with negative 2x equals 2x, and the only way that can be true is if x equals 0, we only get one value of x for which the rational function crosses the horizontal asymptote, and that's the one we already knew about. So that's how you show whether or not the horizontal asymptote is crossed by your graph and can find out exactly how many times it crosses. So now we're ready to do the last exercise in this group, and that is clear this off a bit. Clear it off. Okay, and that's r of x equals 2x squared plus 10x minus 12 over x squared plus x minus 6. So first we'll factor that. We factor the numerator as 2x and an x. So I have a minus 12 and a plus 10. So 12 is going to be, I'm thinking 6 and 2. If I put the 6 here, that'll give me a 12. I'll put the 2 here, 12 minus a 2. So I need a plus 12 and a minus 2. That's the correct factoring. Oh, actually, now I see I have a common factor of 2 up there. That would have made it a little bit easier. So let's factor that out. Let's factor out the 2. So we have 2 times x minus 1 times x plus 6. Gosh, I hope I factored that right. The denominator is x squared plus x minus 6, which can be factored as, let's see, we have x and x. I'm thinking I have to have one negative and one positive. I need the 3 and the 2 with the 3 positive. So there's my factored form. Now let's not forget this leading coefficient of 2 right there. You need that 2 because that's going to affect the end behavior. So first let's do x-intercepts. X-intercepts are the zeros of the numerator. In factored form, we can see quite easily that x equals 1 and x equals negative 6 are the zeros of the numerator. 12 minus 2 is 10. I'm just checking my factor, and I'm a little nervous about it, but I think it's right. Okay, so we have two x-intercepts. What's the y-intercept? The y-intercept, when x equals 0, we get negative 12 over negative 6, which is y equals 2. So we have our intercepts. Now we'll find our asymptotes. Horizontal asymptote, that's end behavior. X is, of course, going to plus or minus infinity, so we look at dominant term. Numerator dominant term is 2x squared. The denominator dominant term is x squared. And that has the same end behavior as 2, and therefore y equals 2 is the horizontal asymptote. Vertical asymptote, zeros of denominator. Denominator in factored form gives us x equals 2 and x equals negative 3 for vertical asymptotes. So now we should have enough information to be able to roughly sketch the graph. So we'll do that. And first we'll enter in our intercepts. X-intercept 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Negative 6 and positive 1. There's negative 6. And there's positive 1. Y-intercept is y equals 2. 1, 2, right there. Okay, now we'll do the asymptote. The horizontal asymptote is also y equals 2. So again, we have an example of a rational function that crosses its horizontal asymptote. Here we go. Okay, and vertical asymptote is at x equals 2 and x equals -3. So here's -3, I think. Yeah, that's -3, and x equals 2, so here's x equals 2. Okay, so I'm just going to make some red dots. We have 1, 2, 3, 4, 5, 6 places where we have to graph. Now we know that the graph can't be in here, because that would mean we'd have to have another x-intercept, which we don't have. So that means that we know that the graph must be here in order for the asymptotes and intercepts to be correct. Similarly, we know that the graph can't be up here because it has to have that x-intercept down there. So it has to cross and have the correct asymptotic behavior. So we got that part. So we have those two branches. Now the center strip is again one of those wiggle things, because this is an intercept, this is an intercept, and we have asymptotes, so the only way we can achieve that is by wiggling through. So verify this graph by looking on the calculator and filling in all the details that you need to fill in.